Dear students, welcome to EPG Pathshala. Today I am presenting before you my module Physical Properties of Soil. Soil consists of organic and inorganic materials, organic matter, water and soil, and the combination of all these constituents give different physical properties to the soil such as texture, porosity, structure, color, etc. Texture, it plays a very important role in soil as it governs the soil behavior also. Texture, it also affects the movement or the holding of water and air in the soil, plus the plant growth, development or establishment of root. All these are also dependent upon the pore size of soil also, and the arrangement of different size particles in units or pads is called as soil structure. Soil structure, it is also important for soil because it modify some of the adverse and diversify effect of texture on soil behavior. There are different soil structure forms. For example, we can platy, granular, columnar and blocky structures are present in the soil. Soil is also having one another important constituent, that is organic matter, which is very important for the formation of soil and for maintaining the good health of the soil. The soil texture and structure, they are both important parameters of soil which governs the soil behavior and the soil fertility. Soil health as well as its biological, physical and chemical processes is deeply interrelated with the plant growth quality. Fundamental knowledge of various soil properties is required for the successful reforestation management of program, and the various soil properties is being shown in the diagram. The another diagram is showing the interaction of soil during various biological, physical and chemical properties. Physical properties of soil. Soil consists of minerals, soil organic matter, water and air. The constitution and combination of these elements greatly changes the soil physical properties such as structure, texture, porosity as well as the portion of pore space in a soil. Consequently, these soil properties change the air and water movement within the soil, thereby affecting the soil ability to perform. Soil also possesses various other properties such as water holding capacity and pH. The combination of these properties make soils beneficial for a wide range of purposes. These soils characteristics decide what kind of plants can be grown in that soil in a particular region. Next is soil texture. Soil texture is considered among the most important physical property that can have a profound effect on various other properties. Texture is the combination of three mineral particles including sand, silt and clay in a soil. These particles vary in size and constitute the fine mineral fractions. Particles with higher than 2 mm in diameter are not considered in texture, although in certain cases they may affect water retention and other properties. The comparative amount of various size of particles in a soil describes its texture such as clay, loam, sandy loam or other textural categories as a result of weathering by physical and chemical breakdown of rocks as well as minerals. Because of these differences in the structure and composition, material will wither at varying rates, disturbing the texture of soil. For example, granite is a slow withering rock which forms sandy coarse soil, whereas shale, which is an easily withered rock, form clay rich soil. Texture of soil influence the soil behavior also, particularly retention capacity for nutrients and water. Sand and silt are formed by physical chemical weathering of the parent rock, whereas clay is formed by the precipitation of the dissolved parent rock as a secondary mineral. The surface area to volume ratio of soil particles and the unbalanced ionic charges determines their role in the fertility of soil, which is estimated by its cation exchange capacity. Clay being the most active, followed by silt and sand being the least active. Then comes soil structure. Soil structure is the arrangement and compaction of soil particles into large clusters known as aggregates or pads. Aggregation is essential for enhancing the stability against erosion, for maintaining porosity as well as soil water movement, and for improving the fertility and carbon sequestration in the soil. Granular structure comprises of loosely packed spheroidal pads that are bounded together mostly by organic substances, which is being shown in the diagram. Granular structure is characteristics of many horizons with high SOM content and biological activities, where large pads in the form of plates, blocks or prisms are characteristics associated with the B horizons and are formed by shrink swell processes and adhesive substances. As soil swells and then shrinks, cracks are formed around soil masses, creating pads which are held together in place by adhesion of organic substances, iron oxides, clay or carbonates. Channels and cracks between these pads are important for air, water and solute transport as well as deep water drainage. Fine textured soil usually have a stronger, more defined structure in comparison to coarse soil formed as a result of shrink swell processes, predominating in clay rich soils and more cohesive strength between particles. The sand and clay particles that constitute the soil rarely occurs as separate particles, but are more or less loosely combined to form aggregates. The type of structure in soils depends to a large extent on the structure and the amount of organic matter in the soil and the way the land is managed. The aggregates that make up the structure may be small in millimeters such as granules and crumbs, or larger in centimeters such as columns and prisms. The granulars or crumb structure is the one favored by farmers and gardeners, as it makes a better bed for the seeds to grow. Soil structure determines its texture, biological activity, organic matter content, past soil evolution, human use and the chemical and mineralogical conditions under which the soil is formed. The soil structure classes have been divided into 4 types, that is platy, columnar, angular and subangular, granular and crumb. And according to the size, very fine to very thin, fine or thin, medium, coarse or thick, very coarse or very thick. Grades is another classification is according to the grades. Grades is the measure of the degree of development or cementation within the pads that results in their strength and stability, which also depends upon weak strength, moderate strength, strong, structureless process. At the bulkiest scale, the force that constitute the soil structures lead to swelling and shrinkage that primarily tends to act horizontally, causing vertical oriented prismatic pads, whereas clay soil, as a result of its differential drying rate with respect to the surface, will produce horizontal cracks, shrinks, columns to blocky pads. Soil aggregation continues as a bacteria and fungi ooze out sticky polysaccharides which bind soil into smaller pads. The augmentation of the raw organic matter which bacteria and fungi feeds upon stimulate the formation of desirable soil structure. The soil chemistry influences the aggregation as well as dispersal of soil particles. Next is the density. Soil particle density ranges from 2.60 to 2.60 to 2.75 grams per centimeter cube and is usually constant for a particular soil. Soils with high organic matter content have lower value of soil particle density and are higher for soil with high iron oxide content. Soil bulk density is equal to the dry mass of the soil divided by volume of the soil, that is, it includes air space and organic material of the soil volume. A high bulk density is indicative of either soil compaction or high sand content. Bulk density is inherently always less than the soil particle density. Next physical parameter is porosity. Pore space is that part of the bulk volume of soil which is not occupied by either minerals or organic matter, but it is open space occupied either by gas or water. In a constructive medium textured soil, the total pore space is about 50% of the soil volume. Pore size changes considerably. The smallest pore hold water too tightly for use by plant roots. Plants available water is held in ultra microspores, microspores and mesospores, and microspores are generally filled with air when the soil is at field capacity. Soil texture demonstrate the total volume of the smallest pores. Clay soils have smaller pores, but more total pore space than sands. Soil structure has a strong impact on the larger pores that affect soil aeration, water infiltration and drainage. The pore size distribution improves the ability of plants and other organisms to access water and oxygen. Larger continuous pores allow rapid transmission of air, water and dissolved nutrients through soil. Next physical property is color. Color is the first impression one has while viewing the soil. Striking colors and contrasting patterns are particularly noticeable. The Red River of the South supports sediments eroded from extensive reddish soil like Port Silt Loam in Oklahoma. The Yellow River in China holds yellow sediments from eroding loose soils. Mollisols in the Great Plains of North America are darkened and supplemented by organic matter. Potholes in boreal forests have variable contrasting layers as results of acidity and leaching. In general, color is determined by the content of organic matter, drainage conditions and degree of oxidation. Whereas it has little benefit in predicting soil characteristics, it is used in differentiating boundaries within a soil profile, defining the origin of a soil parent material as an indication of wetness and water loss conditions, as well as qualitative means of measuring organic salts and carbonate contents of the soil. Next is water holding capacity. All soils have tendency to hold water in their pores as well as on the surface of minerals, grains and structural aggregates. This ability differs from soil to soil and closely relates to texture of soil. Sandy soil cannot hold onto much water and have poor water holding capacity. They are often known as thirsty soil. Clay soils by contrast have many small pores which can be used to store water. This means that they always have some water for plants that grow in them and thus have a good water holding capacity. Soil that can hold a large amount of water support more plant growth and are less susceptible to leaching, losses of nutrients and pesticides. All the water sustained by the soil is not obtainable for the plant growth. Next is resistivity. Soil resistivity is the measurement of soil's ability to hinder the conduction of an electric current. The electrical resistivity of soil can affect the rate of galvanic corrosion of metallic structures in contact with the soil. Higher moisture content or increased electrolyte concentration can reduce resistivity and enhance conductivity, thereby increasing the corrosion rate. Another consistency. Consistency is the tendency of soil to adhere to itself or to other objects, as well as its ability to abstain from deformation and rupture. It is of approximate use in determining cultivation problems and the engineering of foundation. Consistency is measured at 3 moisture conditions: air dry, moist and wet. Under such conditions, the consistency quality depends upon the content of clay. In the wet state, the two qualities of adhesiveness and plasticity are estimated. A soil resistance to disintegration and crumbling is determined in the dry state by rubbing the sample. Its resistance to shearing force is examined in the moist state by thumb and finger pressure. Additionally, the cemented consistency depends on cementation by substance other than clay, such as calcium carbonate, silica, oxides and salt. Moisture content has little effect on its assessment. The measures of consistency border on subjective compared to other measures such as pH, since they imply the apparent feel of soil in those states. Soil consistency is useful in determining the ability of soil to support buildings and roads. More precise measure of soil strengths are often made prior to construction. Another important parameter is temperature. Soil temperature is governed by the ratio of energy absorbed to that lost. Soil temperature ranges between 20 to 60 degrees Celsius. It regulates seed germination, root growth and the availability of nutrients. Below 50 centimeters, soil temperature sometimes changes and can be approximated by adding 1.8 degrees Celsius to the mean annual air temperature. Soil temperature has significant seasonal, monthly and daily variation. Fluctuation in soil temperature are much lower with increasing soil depth. Heavy mulching lowers the warming of soil and at the same time decreases the fluctuations in surface temperature. Soil temperatures affect the anatomical and morphological characteristics of root system. All physical, chemical and biological processes in soil and roots are affected as a result of the increased viscosities of water and protoplasm at low temperatures. In general, climates that do not prevent survival and growth of white spruce above ground are sufficiently benign to provide soil temperature able to maintain white spruce root system. Next is water flow in soil. Water moves through soil due to the force of gravity, osmosis and capillary action. At 0 to 1/3 bar suction, water is pushed through soil from the point of its application under the force of gravity and the pressure gradient created by the pressure of water, called the saturated flow. At higher suction, water movement is pulled by capillary from wetter to a drier soil. This is caused by the water's adhesion to soil solids and is called unsaturated flow. Water infiltration and movement in soil is controlled by various factors such as soil texture, soil structure, coarse matter, depth of the soil, soil temperature, etc. Through the lecture, now we can conclude and come to know that the soil may have or the two soil may have similar texture, but they will have different physical properties. The soil different physical properties such as soil porosity, texture, structure will also governs the movement and retention of water, air and solute within the soil, which will have a determinantal effect on plant growth and the soil microorganisms. The water holding capacity of soil also differ from soil to soil. For example, sandy soil, although it is easy to cultivate, but its water holding capacity is very poor in respect to the clay soil, which has a good water holding capacity and it is very considered to be very good for the plant growth. Further, soil texture, it also plays an important role in nutrient availability to the plants. For example, the tiny silt and clay soil, they are having good nutritious quality in comparison to the clay soil. Although the sandy soil, they are tiny silt and clay soil will provide more nutrient to the plant in comparison to the sandy soil. Moreover, the sandy soil requires more management and frequent irrigation because they are also known as thirsty soil. The differential physical properties of soil such as water holding capacity, texture, structure, pH, it will also governs the region that what kind of a plant or what kind of a crop has to be cultivated in that particular region. Thank you.